So in our next step, we're going to learn to solve these systems of equations. And you may have, again, experienced techniques of substitution or elimination. We're going to prefer to do all of our work in what we call matrix form. So we want to learn how to convert our systems of equations into a matrix form. And a matrix is basically just an array of values. It's a collection of values. And specifically, the way we want to do this is the values need to correspond to the coefficients of the same variable in each column, followed by the final column that contains the constants. So this is from left to right. Okay, so we're going to have each column is going to contain the coefficients of the corresponding variables. It doesn't matter whether you want to do the y coefficients first and then the x coefficients, but the first column needs to contain coefficients for the same variable. The next column to the right needs to contain coefficients for the other same variable. And then finally, once you run out of variables, the final column needs to be the set of constants that we have. So if you look at this one, the first thing I like to do is, even if it's missing a variable, you do have to write a placeholder in there. So if this were just x equals 10, we would want to write it as 1x plus 0y equals 10. Because we do need to have coefficients for all of our variables. In this case, they're both 1. Neither of them is 0, but I wanted to set that up. Now, it might be tempting, and here we might say, okay, that's a 1y minus 2x equals 4, so our coefficients are 1, 1, 1, negative 2. However, notice that the x and the y are switched the terms are switched in the second equation, so I want to make sure that both equations are aligned with respect to the variable. So you don't have to do x and then y, but I'm going to go ahead and do that. I'm going to say this first equation is 1x plus 1y equals 10, and then the second equation is actually negative 2x plus 1y equals 4. So notice we have the coefficients of x, we have the coefficients of y, and we have the constants. And in matrix form, here's what this would look like. We usually use parentheses. You could actually use square brackets like this if you prefer. That works too. I tend to go with the parentheses, but sometimes I mix them up too. Okay, 1, 1, 10, and then negative 2, 1, 4. And that's in matrix form now. Notice that all of the coefficients for the variables are in each column correspond to one another, because we're going to be doing row operations on these. So if we ever combine the 1 and the negative 2, we know that we can do that because they are like terms. They're both x's. Same thing with the y's. We want to make sure that if I ever combine the 1 and the 1 here in any way, shape, or form, that I'm combining like terms. And same thing goes for the constants. But the constants need to be on the right. Okay, that needs to be on the right every time. There's no exception to that. This has to be the constants column. Has to be, because the way our algorithm will be implemented will assume that the constants are in the right-hand column. You could put the 1 on negative 2. You could actually switch these two columns. You could write, because again, the y and x are just the names of the variables. There's nothing valuable or important about them. In fact, a lot of times we just call them x1, x2, x3, and because we sooner run out of alphabetical letters than we would variables in real-world situations. Okay, now once again down here, notice I'm just going to kind of inspect this. It looks like I have x's, y's, and z's. I have 3 variables. Do I have to have 3 equations if I have 3 variables? No, I'm just giving you this example. So in the first equation, I could actually just write the 4x plus 3y on the left and say that that equals 10. It's the same thing, right? Two things that are equal in both directions. We say that has a reflexive property. And then we don't have a z in this equation, but the other equations do. So I want to write a placeholder for the z. It's going to be a coefficient of 0. In the second equation, I can kind of do the same thing, but notice that I have the z on the left. So maybe I'll just write plus 1z here. Now I can either move the z over and subtract the 5, but I think I'm just going to go ahead and add the 4x and then subtract a y. And that is going to equal, leave that 5 on the right, that's going to equal 5. Okay, so I may have to move variables around. Don't be afraid of doing that. Just again, make sure that you decide what order you're going to list your variables in, and then you're consistent about each equation. Down here, this one's already in a nice form. It's just 1x plus 1y minus 1z equals 24. And so that just translates into 4, 3, 0, 10. Again, constants have to be on the right. No exception to that rule. You can switch the columns. I mean, you can't just move one coefficient of x into another column without doing the same thing to all of the values in that column. But, you could do your y's and then your x's and then your z's. But the constants have to be on the right. Okay? And then 4, negative 1, positive 1, 5, and 1, 1, negative 1, 24. There's our system. This vertical line here that I drew and didn't explain, that's not necessary. This is optional. This guy here is really just a visual aid. And that's not used in tech applications. You don't really ever draw that line. Like if you're using some sort of programming language or some sort of calculator, you're not usually going to see these. This is just there as a visual purpose. This kind of represents the equal sign, right? That's where the equal sign would be. And it's just, like I said, a visual aid that is not necessarily going to be there, but it helps to know that your constants are, separated from your coefficients. So that's how we convert a system of equations into matrix form. Just be careful. Quick recap. You want to make sure that you have all of the columns corresponding. They have to be like terms, meaning same variables, and then the constants have to be the terms on the right.